There's
They started doing that.
wow, that's okay. It's in your face. I guess there's no
Yeah.
excuse.
Okay.
Yeah. So, anyways, yeah, if you want, you can just turn off your video for the presentation. It might help with people's bandwidth. There will be a bit of video on my presentation, so it'll help it maybe come in a little bit clear. And then I'm sure everybody's done enough of these things to know just to mute yourself so the barking dog or whatever doesn't cause an interruption. Okay, so what I'm going to do is I'm going to share my screen. Make sure that it's good. Okay, so I don't see what I'm sharing for you now. What do you see? Let's try again.
You got black bubbly looking stuff in the background.
Black bubbly looking stuff. Okay.
Gary, you have to realize that that's the walls of a glaciovolcanic cave.
Oh,
is that what it is?
Take it away.
You'll know that after the presentation, of course.
Yeah. Okay, if everything works, you should see me and some fancy PowerPoint thing that says something about glaciovolcanic caves.
Yeah, looks good.
Wow, that's pretty impressive, Christian. That looks great.
Cool. Okay, well, technology's on my side, which means I suppose we can get started. So thanks, everybody. We're here to talk about glaciovolcanic caves, which, Richard's already stolen the thunder a little bit. The background was, yes, definitely. That's exactly what we're talking about in the presentation. So I'm a member of the Alberta Speleological Society, and we're doing this in honor of the International Year of Caves and Karst, which was declared by the International Union of Speleology, or the UIS. So we've got their logos up there. So welcome everybody to the presentation. What we'll do is we'll talk a little bit about some of the expeditions, but a little bit about the different science that's involved. If you're in the ASS, you've probably seen a few of the different talks that I had done after some of these expeditions, of which there's been a number of them now. So this one, I wanted to talk a little bit more. Now that we've been to a number of these systems, we actually have a better picture of how they develop and how they evolve. So that's a pretty interesting thing. And from the UIS, I'm on the Commission on Volcanic Caves. And as well, the International Association of Volcanology and Chemistry of the Earth's Interior has as well a group that deals with volcano ice interactions, and I'm a member of that group as well. So with that in mind, let's talk about fire and ice. So first off, we'll talk a little bit about some of the different types of volcanoes that are out there. So you might have heard about these in Hawaii that are shield volcanoes. So they are the type that build up over many years over these effusive eruptions. So it's sort of a very slow flow. And you might have heard about these being the tallest mountains on Earth. When you measure them from the bottom of the ocean, they can take that distinction. So you can sort of see the shield volcano shape, which is a gradual rise. So that's actually, I might have mixed them up as to which is Mauna Loa and Mauna Kea, but that's from one side, the side of one looking towards the other in Hawaii is what those two are. And then we have explosive volcanoes. That's the other major type. So you might have seen some of these sort of things crop up on the news from time to time in a farmer's field. So this cinder cone will just rise from nothing. And so you see those as one of the explosive types. All of the glaciovolcanic caves that we've investigated, though, are on this type. It's one of the explosive types, but it's called a composite volcano. And that's the type that is formed via multiple eruption events. So that's an example of Mount Rainier in the United States. And it's actually one of the ones we'll talk about in the talk here today. So what is glaciovolcanism? So there's a couple different definitions out there, but we've taken it to be the interaction of heat from the Earth's interior with the various types of ice masses. So typically on volcanic edifices where it's a magmatic eruption where the lava is now interacting with the ice, but we're finding that there's a lot of other interactions that can happen as well. So traditionally it's been held to be things like subglacial volcanic eruptions, but it can be other types of eruptions where the sort of lava interacts with an ice mass which is nearby, or ejecta from the eruption lands on ice, or different things. So there's many different ways that glaciovolcanism can occur. So what are glaciovolcanic caves then? Well, this is interesting because we've known about these types of caves for over 100 years, but there hasn't really been a consistent nomenclature for them. But this image here might give you a little bit of an idea of what we're talking about. This is heat from volcanoes interacting with the ice mass to form void spaces, i.e. caves. So this is kind of a look at one of the entrance zones where we can actually see the heat and the steam rising up from underneath a glacier. And so we can see that cause cave entrances to form in the ice. And this is what we've been exploring as we go into these cave entrances and we're conducting various kinds of research. And that's what they look like from the inside. So you might have heard of glacier caves or end glacial conduits or other types of glaciology related caves, which are formed by water dissolving or interacting with the ice. Typically, water comes from melt from above, whereas these are formed by heat or steam or thermal emissions or thermal waters that come from below. So the ice is being melted from below. Typically, they're not totally in ice. They have a rock floor, and that's the volcanic rock, which comprises the floor, and the ice, which is the walls and the ceiling. So we've started using the term glaciovolcanic cave to represent those. And that's partly because there's just been lots of names. We've heard of glacier caves, we've heard of steam caves, we've heard of other things. Fumarolic ice cave is another one, which I think still applies to many of the types of glaciovolcanic cave that we've seen. But basically, it's really because there's the different types of ice or snow or different cryospheric mediums that the thermal emissions can interact with. So I didn't really have a good snow picture, but you can get the idea of a cave could form in snow, right? Or the top layer of a glacier can be snow, right? So you get maybe a cave that could form in there. And then we have fern. So fern's that part of the ice world, which is in between snow and in between ice. So it's getting compact. The density is getting compacted, and we can see caves that are in fern. So we get a dense ice-like substance, but it's not quite considered ice yet. It's just not that compact. So those are two examples there. We've seen caves in snow and in fern. And then we get ice as well. So we can have the traditional kind of ice that you'd expect from frozen water, a frozen waterfall. They can create speleothems within the caves, and that's an example there. That's Katie Graham admiring one of the ones in one of the caves in Mount St. Helens. It was a frozen waterfall. We started calling them cryospeleothems, just I think because it sounds cool, but really it's just an ice formation in the cave. So we get those, but the really interesting part is when the caves get really deep into the glacier, they can form in glacier ice as well. So it's true glacier ice where the density, it's been compacted over many years, and it meets that criteria of glacier ice. So we can see that as well. So those are the main types of mediums that we can see glaciovolcanic caves form in, and some of the imagery of some of the ones that we've seen. So here's the thing though, there's actually, so they've done some studies, Edwards and others did one that found there was 245 Holocene volcanoes around the world that have potential for volcano ice interactions. Now, how many of those 245 do you think contain glaciovolcanic cave systems? The answer is that you can see them in red on this diagram. And when you count them up, there's actually not many. The Pacific Northwest, United States and Canada. In Antarctica, there are some confirmed systems on Mount Erebus and Mount Melbourne. And then there's the yellow ones. So those red ones are the confirmed ones. There's not that many. The yellow ones are the ones where there's some evidence of them. There's been anecdotal reports, but no in-depth study or no peer-reviewed studies that we found. So really, despite the lot of potential, there actually are very few locations where they've been studied and known about. So we're really just we're really in a golden age of discovery of glaciovolcanic caves, because you can see there's a lot of yellow ones there that are potential sites for study. And we're still, have our hands tied with all the ones that are in red. So I've been lucky to be part of a number of expeditions where we're doing some investigations of these glaciovolcanic cave systems. And that's partly for the exploration aspect. That's how I've been involved in them, is as an explorer and a caver, just being part of the survey teams, leading survey teams and that sort of thing. But that's evolved a little bit different into getting into more of a speleological understanding of the caves. So one of the things, we know so much about karst caves and solution caves, where the mechanism of formation is the dissolution of soluble rocks. There's so much we know about that. Still a lot we don't know, but there's so much we know. Whereas these caves, for many years, it was like, well, it's obvious they're formed by volcanic heat and gas, and that's kind of it, right? There has not been that much in-depth investigation of their morphologies and their longevity as well. So that's one of the things we do, is we are looking at the systems as they grow or change over time. So that's one aspect that we're looking at. Others are the geochemistry. So we're finding out how the caves and volcano ice interactions impact the hydrothermal systems of the volcanoes. So is there a chance that the presence of caves, is a barometer for volcanic activity, or is it going to influence the volcanic activity by inclusion of, more meltwater? How does the gas interact with the ice? Is that going to cause any changes? So that's one example there. We do climatology studies as well. So just to find out more about the microclimates, the airflow. You can see in these images the ablation scallops in the walls. And these are formed by airflow, similar to how paleo water flows had formed scallops in limestone caves, right? So what we found is actually nobody's actually studied the scallops of this type of cave, whereas you can imagine that there's been a lot of study of scallops in karst caves. So, these are areas that are truly just pioneering here. I talked a little bit about the survey. Obviously, that's a big component. In order to study these things, you have to know where they are first and that sort of thing. And we're doing a lot of other things we'll get into more detail down the road. But just to give another overview, I'm not going to read all of this to you, but we're looking at seeing about the relationships, volume changes to the caves, to map the caves and find out if there's any hazards, because you can imagine a cave formed by volcanic gas might be dangerous. So there's definitely a search and rescue aspect to that as well. And then the middle point, which is one of the most interesting to me, is that these subglacial environments are a good analogy. They're an analog two cave systems that might exist on other planets. So we look at the icy bodies of the solar system, moons of Saturn like Enceladus, or Europa, moon of Jupiter, that we know have liquid oceans and ice surfaces and a source of heat as well. So are these a good place to look for life? And can we learn about these type of caves to learn more about where we should look for life in the solar system? And we are working along that line with some of our research partners to discover those things. So this diagram shows a little bit about some of the different influences. So on the bottom, we have the cave morphology. So that is influenced by the middle part, the hydrothermal system. The geochemistry is influenced by the hydrothermal system as well. The cave climate on the left is influenced by the hydrothermal system as well. But all of those things influence the microbiology, the environment of the cave and what can live there. So those are all have an influence on each other. And that's why we have an integrated study. We have researchers who are climatology specialists, volcanology specialists, and all sorts of things in order to better understand these environments. So let's go into one of the expeditions. We've done 3 expeditions, 3 major ones and 1 small one to Mount Rainier. So what do we have in Mount Rainier? It is a very tall, 4,392 meters high stratovolcano in Washington State. It has the largest single peak glacier system in the lower 48 states. So sorry for the imperial measurements, but that's 1 cubic mile of ice covering 35 square miles. So we can see what that looks like in the USGS diagram there. So one of the issues though is that Mount Rainier is a decade volcano. That is one of the volcanoes that the International Association of Volcanology and Chemistry of the Earth's Interior has determined is one that needs additional study due to its danger, due to the amount of people that live nearby and so forth. So they've done a sort of a study and classified a number of volcanoes as decade volcanoes. And those are the ones that are sort of the ones to watch around the world. And yeah, the issue here is that volcanic mud flows, the sudden eruption and the dissolution of 35 square miles of ice would cause lahars, these volcanic mud flows that would travel down the various valleys all the way to Puget Sound. And of course, there's a number of towns and cities that are on the way. So it's definitely a concern that, you know, any sort of eruption would be very impactful to the area and the residents. So Mount Rainier has 2 summit craters, an east crater and a west crater. And through a number of expeditions, we camped in the crater for a week at a time in order to do further studies of the glaciovolcanic caves within the crater. So that's an image of the east crater there. So the east crater is more defined. You can kind of see it slopes, but it's very well defined. The west crater is on the right-hand side of this image, less defined, but more volcanically active. Okay, and so we'll talk a little bit about that later. So yeah, you can even see our research camp. One of our pilots actually flew over and provided us these photos. And you can even see the line of climbers that is sort of making their slow way up the mountain. It's about a 3,000 meter elevation gain. People take 2 or 3 days to climb usually. And the caves have been known about since the first ascent. It was in 1870 that the first ascent party actually reached the summit, and had it not been that they spent a night sheltering in a steam cave, they might not have survived the attempt. So they've been known about for a long time. It wasn't until 1970 that famous mountaineer Lou Whitaker and Lee Nelson made the first hand-drawn map of the steam cave system, and that's on the top. Now, only weeks later, a survey via compass and tripod produced the bottom map. So if you're interested in cave surveys, you can kind of see what the difference is between using a compass and using basically a sketch map that you drew as you made your way through the system. There are some similarities, definitely some similarities here, but you can definitely see the orientations of some of the passages are quite a bit different. So this is the world's largest glaciovolcanic cave system. So as of the 1970s, efforts mapped by Bill Loki, Bill Steele from the NSS, and a number of other folks were involved in Project Crater. So they actually had a helicopter up and spent a lot of time to map out the east and west crater caves. And at the time, yeah, definitely there weren't many known in the world. So it was pretty easy to say this one was by far the largest. And so, yeah, two distinct crater cave systems that do not connect together. Now, this is the current map. So this was the survey superimposed on Google Earth. So we can see the east and west crater cave there. Now, one of the things you might notice is, so on the east crater cave, have a look at the west side. So you can see the west side branch there. And then if we look back to the west branch of the East Crater Cave from 1970, you can kind of see it didn't exist, which was an interesting finding. So we found, that not only is the cave longer, just via maybe better survey or different, more thorough survey, but it has actually grown in some case there on the west side. So it's really interesting that East Crater Glacier is a trapped ice mass. So it is a glacier that doesn't flow anywhere like other glaciers. It's trapped within the crater. So it's a very unique place to try to do studies to see what is happening there. The West Crater Glacier does breach the south rim, and it does flow. Okay, so there's definitely a difference there in the two types. As I mentioned, it is a bit of a climb. We did a number of expeditions to the top of the summit there. And in each of those, we were not allowed a helicopter to do studies like they had been in the past. So that literally meant 50 to 100 people on these cave expeditions, most of which were people who just volunteered to help us out to go to the top and porter equipment. And there were a number of folks that actually helped from Alberta and BC even, who came and made the trip. So I remember that Peter Norris was there, Jason Levine from the ASS, Mehdi Bukal, who some of you maybe know as well, were all helping with the project to sort of carry equipment up or down. And that was crucial because we couldn't have done the studies. We literally had 1,000 pounds of equipment between all the scientific equipment and other stuff that was necessary. So kudos to everyone who lent a hand to the project. So here's an image of what the entrance zones look like. So a lot of steam coming out and these entrances all around the crater rim, and then they descend steeply 35 to 40 degree slopes on these volcanic breakdown boulders that get deeper into the cave. All right, so one of the things that we do is we try to map out the fumarole location. So how are these caves formed? Most of them are fumarolic emissions. So we have heat and gas by these fumarole vents, and using thermal imaging, we can find them fairly easily. Although sometimes you sit on a rock or put your hand on one and you can tell when you're near a fumarole, whether it's an increase in the humidity or the temperature, and that suddenly it's a little bit warmer and you can sort of say, oh, I'm by a fumarole. And that's what it is. We've seen fumaroles of 50 degrees Celsius. We've seen areas of just warm ground, warm sediment in the cave. But this is an example of an actual vent. The white hot part there is the actual vent, or the core of where the heat is coming out. So definitely interesting there. And then tie that to the anemometry. So we can actually deploy these anemometers. They were one of the heavier things that was brought to the summit in order to do the climatology work. So these will measure the airflow, the most minute changes in airflow, in the temperature, the humidity, and all of those factors, which help us to determine how these caves are forming. How are they sustained? So, we have not only a fumarolic emission and heat to melt the ice, but then we have the airflow. So part of it's maintained by the advection and the chimney effect of having higher and lower entrances and so forth. So one, they have to form. Two, they have to be maintained and not collapse or not, freeze over again. So there's definitely a combination of factors that's going on. So this is the largest chamber. It's called the Colosseum in the East Crater cave system. Definitely an amazing place. And these caves are truly like being on another planet. It's such an amazing experience to be underground in this. You're under a glacier inside the crater of an active volcano in a cave formed by volcanic gas and steam. You've got water dripping on you from above, steam and heat coming at you from below, loose rocks everywhere that tend to tumble around to the bottom of the chambers and so forth. And yeah, definitely it's an amazing experience. Within the East Crater Cave at 14,200 feet is this lake. So a lake had been found in the West Crater back in the 1970s, and it was declared the highest elevation lake in the United States or in North America. And so funny that lake appears to have disappeared. And what we found was a new lake. New lake was found in the East Crater Cave system at 14,200 feet. This lake is seems to be persistent in that cave, and so now it sort of holds the title because the other one has apparently disappeared. So we're also doing studies of the ice cap there. As we said, it was sort of a captive glacier. And one of the studies in 2000 had placed ablation markers in the ice and found a movement of 2 to 3 meters of ablation a year. One of our projects was to do a repeat of that and install ablation markers. We actually had a whole line of ablation markers that were installed in the wall of the Colosseum. The idea being that we would go back within a year and be able to measure this row of ice markers. Here's the thing. The top one was an ice screw at 8 meters above the deck. And the ice screw in 1 year was found crushed against the rocks at the bottom. So we actually found, if you calculated the movement and the amount of days, it was a minimum of 8.4 meters a year. And that was by the year 2016 when we did that measurement. So what does that mean? Does that mean that the ice in this captive glacier is melting more rapidly? And what does that mean? Well, I'm not qualified to answer that. And certainly our ablation marker study was done only in one part of the cave. So it can't be representative perhaps of the whole crater, but it was an interesting finding to see such a difference to the earlier studies. So what do we have now? What was in 1970 mapped at about 17 to 1800 meters is now 3.5 kilometers in length due to the efforts of our teams over 2 years, 2015 to 2017, when we did this project. And so that is not necessarily indicative that the cave has grown. Perhaps it's, we really got into every nook and cranny is kind of what's happened. But definitely doing comparison to the previous years, we can see that west side, that whole branch on the west side is new. So that is an interesting thing to report. And the depth at 144 meters is fairly significant. So we can see in the 3D model imagery, which is nice to look at, the rotation and how the cave system conforms to the shape of the crater within. So, and we can see the one room at the bottom there is called the bird room, and that's the lowest part of the system. The deepest part there, and then the tallest part is up alongside the west side of the East Crater Rim. So that's the imagery there. So interesting stuff. Hopefully you're still with us, and we can move along to talk about Mount St. Helens. We'll take questions at the end, of course. We'll have time for that. So if you do have anything, just keep them in mind, write them down, or whatever you need, and we'll talk about it there. So Mount St. Helens, of course, is very famous due to the fact that it is the eruption that happened in May of 1980. So it's just been over 41 years since the eruption of Mount St. Helens, which was the largest volcanic disaster in the history of the United States as a country. So definitely a huge, impactful event. People who are around, can say that they collected ash from their their sidewalk or things like that. So certainly there was a lot of impact beyond just the local area. Volcanic mud flows, those lahars, definitely were impactful to some people very far away from the eruption as well. So not only was there a massive local impact of the sort of sudden release of 25 kilotons equivalent of nuclear energy, this lateral blast, which actually blew the top and the north side of the mountain away and caused a massive amount of destruction. I want to say it was about 500 square kilometers of forest that was destroyed, trees knocked down, and so forth. And so here's an image of the crater as it existed. This image only a couple years old. So here's the thing, you can see in the crater that there has been a lot of change since 1980. One of them is that there's the formation of two lava domes. So just behind me is the 1984 to 86 lava dome in the front, and then a 2004 to 2008 lava dome sort of behind it. And then the scale of this, the width of the crater at its widest part is about 2 kilometers. So we have not only we have two successive major periods of eruptive activity since then, we also have the formation of a glacier. So since 1980, snow accumulation in the crater has been sort of, it's a larger catchment area for snow than the surface area is, because snow doesn't cling to the crater walls and it just sort of sloughs off and builds up around the two lava domes. So we have not only that we have this additional surface area to catch snow for glacier building, but we also have another effect, and that is that a lot of rock fall from the crater rim actually settles on top of the glacier and helps sort of shield it from some of the melting. As well, we have a lot of storms and weather that's specific to the crater. So we have, weather might hit and the snow will deposit in the crater and not outside of it. So it sort of catches snow. It's been described as a perfect glacier factory. And for that reason, it's one of the only advancing glaciers that we know of. So it's interesting that it's advanced at up to 3 feet per day at its height. And that is an amazing thing to hear about, especially when a lot of glaciers, most of them in the world, are being said to be in retreat. Inside the crater is an amazing place. It's like being on the moon. It's sort of like this neat, steamy environment in bad weather. You see these volcanic rocks sort of propping up around you on the glacier. And it's definitely sort of, even when you're outside of the caves, it's an amazing place. So we're lucky to have a research permit to go in the crater because it's off limits to the public. Strangely enough, the USGS thought that going into the inside the crater under a glacier in an active volcano in caves formed by gas and steam was an okay thing. So yeah, we've been granted a permit for our research. So one example of that rock fall that I talked about is you can see in the image here all of the rock that's sort of been deposited on the glacier. And that just builds up every summer. So every summer there's going to be, in the glacial building process, a layer of rock and debris and dust that's formed. And then every successive winter, we have additional snowfall that covers it. And we see that in the caves. It's truly amazing. And living in the crater, it was described by one of our team members as like living in a bowl of Rice Krispies. You could hear 100 of these rock falls a day. And you probably wouldn't be able to count them all, but you can see a little bit of them there. And I've got a couple more maybe zoomed in where you can see a few more. And this is just constant to the point where since the eruption in 1980, they say the crater rim has lost 16 feet in height. So, so not only did the eruption shave the top of the mountain off, but since then we actually see quite a bit more dissolution of the crater itself, and that's happening everywhere, all throughout the crater. We see these rock falls. Luckily, though, most of the caves are around the 2008 lava dome and are sort of away from where the rocks get deposited. So we still see rocks within the cave, in the ceiling and in the walls, but not to the extent it could be. So certainly there's areas where they say 15% of the glacier is actually not ice, it's rock. So the studies in Mount St. Helens started after this sighting. In 2012, an overflight of the glacier saw a hole had formed in the glacier. So that was seen by members of the Mount St. Helens Institute, Jared Smith, and a pilot took this photo. And then that's what started the project. So Eddie Cartaya from the National Speleological Society and Brent McGregor, these are from the Oregon High Desert Grotto of the NSS, had formed a group called Glacier Cave Explorers, and they decided they would do some studies of Mount St. Helens, Mount Rainier, and Mount Hood. And it's under that umbrella that we've done basically all of our work on those US volcanoes. So that hole was first entered in 2014 and given the name the Godzilla hole, because what else would you name a hole in a glacier belching volcanic gas that's, obviously sizable? It's the type of thing that Godzilla might climb out of. And so since then, we've explored quite a number of caves over the, I guess it's been 8 years now of this project, to what started with the Godzilla hole and another cave named Crevasse Cave explored in 2014. We have thoroughly, explored the areas and found quite a few more. So here's an example of one of the fumarolic areas with a number of cave entrances that we have found there. So the anemometry is obviously ongoing in Mount St. Helens as well. And the survey is ongoing as well. So we see very similar types of morphologies, but also some different types that we've noticed too. This is another image. So we have a video of some of the fumarolic areas. So we have fumaroles here that are up to 92 degrees Celsius. And so we actually believe this area, the cave formation has been prevented in this area. And you can see the slope of where the glacier adjoining the lava dome sort of it has become fractured, and we have this sort of glacial depression where now there's an ice-free area. And I think it's simply because that area has constant heat, and there's a number of cave entrances adjacent to that area, which is really interesting. So we see, as I mentioned, some rock and layers of debris in the ceilings and in the walls. And that's interesting because they can melt out when we're in the cave. They can literally, some places are like a shooting gallery that they melt out while you're standing nearby. And that's something we have to look for. So after about 7 years of exploration, we had 10 distinct caves identified, mostly around the 2008 lava dome, which is interesting because at Mount Rainier, the caves sort of parallel the crater rim and the entrances rise towards the rim. Here, they parallel the lava dome and entrances rise towards the dome and not towards the rim. But they follow a similar pattern, which is interesting. Here's the survey of two of the caves that we have, or one of the caves that we have multiple years of data. There's one omitted in the middle, but we can see the growth on the north end. Actually, we see over 100 meters of extension of the cave in only a few years. And that's due partly to the buildup and the advancing of the glacier. So we have an environment where the medium for cave formation is growing. So imagine if you could have more limestone deposited every year and the cave formation only took a year. Well, the cave could grow in the same extent that it can in this ice mass. The top entrance of this cave here was an entrance because that's where the glacier ended before. Whereas in only 4 years, now we have a lower entrance than that one at the top end of the map, and that's because there is now ice for caves to form and fumarolic activity to cause them to form, which is interesting there. So this, I don't know that there is a comparative cave system anywhere in the world that is forming and growing so quickly, other than perhaps some englacial conduits and glacier caves that are forming very rapidly via water melting, causing some huge channels. But this is definitely very interesting. So we can see some of the caves, how they would have grown just simply due to the advancing of the glacier against the dome or around the dome. So some of the cave formation is simply due to that there is more glacier for caves to form in, not necessarily because there's more volcanic activity. So that's the part which we still have to study, I think, a bit more to be sure about that. But certainly a lot of it does appear to be related to just more glacier. So this is a number of 3D profile images where we can see a consistent cave morphology, where the red lines in the morphology there are showing the angles which show the caves building against the side of the lava dome, entrances rising towards the dome with sort of master conduits that are lateral to the dome. So you can see a number of them that sort of displayed that morphology there. And then we had some theories about the formation as well, and did up a few different diagrams to show this is specific to the Mount St. Helens caves, because we can see the debris layers for every year as well. So you would think that heat rising would cause a chimney to form. You just have a hole which goes straight upwards to the surface. But what we found is that isn't the case. In most cases, the caves are adjacent to a slope. And not only do you have that chamber, which could form a chimney to the surface, a lot of the exchange, the advection and the heat is following the rock ice margin to basically make entrances at the rock ice interface of where the glacier and the rock meet. So we see a number of different passage morphologies that are coming from this. So here is a case where we did have a chimney form in a cave that previously didn't have one. We had a very high roofed chamber in one of the caves, and in 2020 it actually had breached the surface. So we have to look at this a little bit more. Well, again, was that an increase in heat output that caused the breach, or was it a decrease in glacier, right? Is there was there less snow that year? Like, what was happening there to cause that breach? So this breach was in September of 2020. We were just back there 2 weeks ago, and this hole wasn't present. It had entirely snowed over. It was, you couldn't even detect that it had been there. So definitely these are very dynamic systems. One of the things we did most recently was one of our partners is the NASA, the Jet Propulsion Lab, and they test some of their precursor robotic technologies for exploration of some of those icy worlds that I was talking about. So one of the things, they have access to some fancy LiDAR. So this is a Leica BLK 360 that they brought along, and I was able to get a little bit of time on it. So it's really neat, paired with an iPad, so you can see how your scans are actually doing as it goes. So it creates a point cloud, and the highest resolution scans take about 6 minutes per scan with a maximum range of about 60 meters. Now, in these caves, there's a lot of steam, and that does definitely mess with the sensor. So one of the things we found is that the way to mitigate that was to do more scans closer together. And if you can have the iPad and see kind of where you might be missing data, you can kind of make up for it as you go. So it is, I think, a viable tool for doing this type of survey. The $20,000 price tag is a bit of a barrier, I think, to most cavers. But one day, hopefully, the technology will become a little bit better. So I'm moving an image over to the screen. If somebody could unmute and tell me if that's actually like, is that coming through?
Yep, it is, Christian.
Okay, perfect. So yeah, I just got this data. So I apologize. I'm not able to kind of play with it too much, but this is an image of the point cloud of one chamber of the cave. So here's the thing, is that in the week of time, like the NASA guys had some other duties. They were able to partially survey one of the caves using the LiDAR system, whereas we were on Disto-X and using TopoDroid for the remainder of our survey teams, and we were able to survey, well, much more, right? Perhaps not the detail, and you can see the ablation scallops in the image, right? So you can definitely get some very accurate data from this method, but certainly, and maybe in the hands of proficient cavers, perhaps the process could be quicker. But certainly there's limitations, but there's definitely some amazing things that the LiDAR does, and especially the BLK 360, because it can give you temperature data. It can do photogrammetry of the walls. Again, that was a limitation because of light, and that the caves weren't necessarily lit up to get the color imagery to pair with the point cloud. All right, so definitely that was the NASA partnership. The other partnerships we do are on the biology side. So this is Rick Davis and Roberto Anatori, two of the astrobiologists that we work with, and I've been very lucky to collect samples and be part of their studies to look at sediments, typically in the area of fumaroles. So they're looking at the sediments in the area of the fumaroles, and what they're looking at is, well, what sort of microbial communities might be living in this environment. So they actually, in one of the papers that they did on Mount Erebus caves and the microbial communities there, they came up with a term called DOVES, which is dark oligotrophic volcanic environments. And that's one of the ways that they describe them as analogs, is they're oligotrophic, so low nutrient, dark or low light, and volcanic, meaning that there's some sort of heat or gas that is present in the environment. And so what their studies involve are these analogs, or these proxies for extraterrestrial microbial life in Martian and lunar caves. They're analogs for subsurface marine environments as well. So you've heard about hydrothermal vents at the bottom of the ocean that have very interesting extremophile bacteria. And of course, these caves, we are the first to enter them. So they are pristine with little to no human impact. So they're a great environment for doing some unique studies. And so what they're doing is a number of things. So the sediments get analyzed. So there's some geochemistry involved as well. So what's coming out of the fumaroles? What's the composition of the gas that's coming out? What are the microbes that are there? What are they doing? So they're going to do a taxonomic identification, but also metagenomic sequencing, which is a very powerful tool to infer the metabolic lifestyle of communities of bacteria. So from this, they've actually done a number of analyses of bacteria from Mount Erebus and Mount St. Helens. And I sent them a sample from the booming ice chasm in Alberta, which was, it'd be an interesting comparison to these types of environments as well. So they actually have a grant that they got a grant to do a study on a number of these dove environments, which was, they said it was the largest grant to study to do metagenomic studies in a cave that had ever been granted. So it's a big study. So not only are they looking at the astrobiological effects here or components, but also as you probably aware of the antibiotic component. So the worldwide fight against antibiotic resistance, and that caves are a good place to look for microbial communities that have antibiotic properties. Well, here's an example. They actually have a program where they involve the college students to help with determining if some of the cave microbes have any antibiotic properties. And they have found some of them hold promise for antibacterial activity. And we can see I'm spacing out on the word. If it's an exclusion zone, you can see the light area around the bacterial community, which means that it's fighting against the infection or the bad bacteria that's in the dish there. So they do these metagenome assembled genomes and find the different types of communities that are present in the samples. So here's an example of the different types of bacterial communities from one of the samples. And then if I look, there was a couple in there that were in bold that weren't characterized separately. They found 2 viruses, which is kind of cool, except for the part where I asked if we're all going to be part of the zombie apocalypse. And I think the answer was no, but one can only hope. Okay. So Mount St. Helens, one of the largest caves was Mothra Cave. And this was over 500 meters in length and 60 meters in depth. And it's one of the ones where we've done the most studies due to its accessibility to us. And that, it was one of the major ones we discovered in 2017. After the first 2 had been discovered in 2014. So Mothra is kind of one of our sort of favorites to go to for some of the studies. Now, here's the thing. It had been one of the largest in the crater, but we had since actually discovered many more. So at the end of 2019, we had 10 distinct caves at 2,200 meters. One of them on the west crater side, this is the one that's kind of in pink. We named it Rodan. So if you notice, there is a bit of a theme here. And I had to learn a heck of a ton about Godzilla in order to name these things, because it started with the Godzilla hole, which I had no part in naming, and then sort of had to continue the theme, I suppose. And it's meant learning a lot more about Godzilla monsters than I ever thought possible. So here we have Rodan Cave. We actually ran out of time in 2019 and only did the major passages, and it was 470 meters, but we knew it was going to be significantly more than that. So our last expedition was literally like 3 weeks ago. We were in the crater for a week, and we discovered 3 more caves. So here's the latest updated imagery from, I put all the cartography together. We resurveyed Mothra Cave because it's changed quite a lot. We resurveyed Rodan Cave, and we found 2 more. So 13 total. So the new total, I didn't expect we would do this, but we cracked 3 kilometers total of caves, which is amazing. Rodan Cave is over 770 meters long, making it the second longest glaciovolcanic cave in the world after the Mount Rainier East Crater System. And it's over 80 meters deep, which also makes it the second deepest cave of this type in the world. The other thing you can see is, as we've discovered more caves, you can kind of see how they wrap around the 2008 lava dome. Now, here's the thing. These caves, mostly from what we've seen and comparative satellite imagery has shown, is that they only started growing perhaps 10 years ago. So as the glacier grows, is there a chance that these caves may all eventually interconnect and form a system even larger than the Mount Rainier system? Perhaps. It's one of our theories, is that the lateral expansion of the systems will continue, along with the expansion of caves, passages that go up towards the lava dome as the glacier builds up in elevation against the dome as well. So definitely interesting thing to see. Here's an image. I plotted all of the caves together on the same project file so I could make a little 3D image and spin it around because it looks neat. And so that's all of the caves around the lava dome. Rodin's there, just there in the front, the long sort of skinny one. And then ones that were actually near our camp are the purple ones at the lowest elevation. Purple, the lowest elevation. Red is the highest elevation in that imagery. So we're pretty excited about that. Now, Canada has its own glaciovolcanic caves, and they're at the Mount Meager volcanic complex, which is formed due to the subduction of the Juan de Fuca plate underneath the North American plate, which has caused the Garibaldi volcanic belt and these Pacific Northwest volcanoes to form. So Mount Meager is better known as well as the Mount Meager volcanic complex, and it has been called Canada's most dangerous mountain. So you might be familiar with the 2010 landslide that happened there, that at the time was the largest landslide recorded in Canada's history, with over 53 million cubic meters of rock that had come off one of the slopes to Mount Meager adjacent to the glacier. So that slope itself was a pretty massive landslide. However, studies since have found over 25 additional unstable slopes. So these unstable slopes are a bit of a concern, obviously due to the chance that they may cause some additional landslides. The other thing that they've done some modeling of the debris flow of an eruption. And so different models of different amounts of debris flow can be modeled. And one of the extreme extents is that the debris, and historically, eruption debris has reached and buried the current site of the town of Pemberton. So this new model is not unrealistic to say that the debris flow could reach Pemberton once again. The last eruption was 2360 years ago. Okay, so it wasn't that long ago. And of course, this being Canada's only current active volcano, well, we have to consider that this could obviously happen again. So tephra and ash modeling would show that there's definitely another impact there, a large magnitude eruption. Large being, this model is based on a VEI, volcanic explosivity index of 5, which would be equivalent to the Mount St. Helens eruption. So an equivalent eruption would cause this amount of ash and debris based on 2 different wind patterns that you can see modeled. So not only do we have the landslide risk, we have the lahar and the volcanic debris risk. We have definitely tephra, ash. We have a pyroclastic flow. So the actual lava flow might be only contained to that area. But there's over 2,500 people that live in Pemberton and another 2,500 that live in the valley. So there are some concerns. And a volcano does not have any official government monitoring programs. So it's definitely a candidate for some further study. So here's the thing. In 2016, you can just see what is now known as the entrance to Canada's only glaciovolcanic cave systems. So it's quite a large entrance actually that formed in the Job Glacier. And so we can see it there with some of our folks for scale. You can see the imagery there. So what complicates this cave is that it's not just steam coming out of the cave entrance. There is a fairly significant component of hydrogen sulfide. And that is why the researchers had never entered the cave. It's obviously that's toxic to humans. They found dead birds on the glacier. It's just not conducive to human exploration unless you have the right equipment. So it was only a couple years ago that we teamed up with these folks and had a team. Some of our team from Glacier Cave Explorers from the United States came up with us, and the 2 Canadians, myself and there's Katie Graham, went to try to enter and survey the cave. So we had with us some technology that was loaned to us for the purpose. This is an eLabs system, which is made for confined spaces and, shooting terrorists and things when after you gas them with tear gas and stuff like that. So anyways, they had lent us the equipment, but without all of the other cool stuff that might go with that. We tested the equipment in Mount St. Helens, partly because we used it at the summit of Mount Rainier. So the West Crater Cave at Mount Rainier, I mentioned, is more volcanically active. We have actually found pools of carbon dioxide over 20% concentrations in ambient air. And so we used these systems to fully explore the West Crater Cave of Mount Rainier. And then we sort of felt they were okay enough to give us a little bit of air to do what we might need to do in the other system. So here's just a video of some of the testing in Mount St. Helens. I think you get the idea. You kind of sound like Darth Vader and you're crawling around with this thing. So again, a bit showing the scale of the massive cave entrance at Mount Meager. So the purpose of the study was to try to get temperature of the fumarole vent, because if they know the temperature of the fumarole vent, depending on if it's 300 degrees or 50 degrees, like we've seen on the other volcanoes, that can give some indication of how close the magma is to the surface, as well to know the composition of the volcanic gas. So we can measure it at the entrance, and that's diffused with ambient air. If we can measure it closer to the vent where it's coming from, we know that sulfur dioxide is more indicative of, I guess the danger, perhaps is the best way to put it, of the magmatic system. Whereas if it's strictly to H2S or carbon dioxide, then there's less cause for concern. So yeah, we were there a couple years ago, and unfortunately, we weren't able to complete the project. This was me swinging over the moulin, which had formed in between the sort of balcony to the entrance and then the entrance itself. So this is the limit of exploration in the cave there. So we have hopefully some opportunity to go back and explore with a different breathing apparatus. So these things give you, they give you 45 minutes to an hour. But we adopted sort of a cave diving protocol and a rule of thirds, which really meant 15 minutes of exploration, with 15 minutes to do our work, which was really not a lot of time. So a rebreather-based self-contained breathing apparatus system would give a lot more time, but that needs a lot more funding. So we're hopeful for that. Okay, so that was in 2019. And the entrance that you see there was the one designated 1A. Okay, so this is in 2020. So about a year later, we see another massive chimney has formed, 1B. Number 2, we knew about before. That one we hadn't entered. And now there's a number 3. So in a year, there has been significant change in the system. And so we're actually hoping to go back very shortly in order to just get eyes on, because nobody's seen it for over a year. So it might have even changed from this image. And that'll help us to plan for 2022, which is when we actually hope to go back. I'll finish off very quickly here with just a bit about the NASA components. So Iceworm is the ice climbing robot that JPL produced, and we tested for the first time, the first complete field test in the Glaciovolcanic cave, the world's first ice climbing robot, which was pretty awesome to see in action. So it's kind of like a slinky, I guess, uses 2 commercially produced ice screws to anchor to the wall, and it can sort of climb. And the idea is there was another system they tested with us at Mount Rainier. And that one had a number of cartridges, essentially, where it could take and cache samples of ice that it takes. So one of the ideas to drill into the ice and look for microbial communities. So moon diver is another concept that they have under development. A number of lava tubes and cave entrances have been observed on the moon and on Mars. Sheltered from the regular solar radiation, these may be prime candidates to search for life or signs of past life. So Axel rover is another concept they have. It's a rappelling rover that would rappel down into lava tubes and do some exploration there. There's a number of other ones. If you do a search on the internet, Daedalus is one that the ESA, the European Space Agency, is developing. And then one that these guys are really keen on JPL is called EELS, which I would butcher the acronym. Everything has to have a cool acronym, by the way. But EELS is the Enceladus something life surveyor. And that one is meant to go into cracks and crevasses and things and basically do the same thing on the icy worlds. So the partnerships that we have are pretty amazing to be part of and see. On our last week there in Mount St. Helens, they were testing a digital holographic microscope. So it looks at the surface of ice, and the idea is they're trying to determine what clues the surface might have for where they should actually drill and take samples. So I'm very hopeful to see the results from our latest trip to Mount St. Helens. Okay. I think we can call it there because it's been an hour, and I hope you're still with us and we're entertained and heard a little bit about some of the exploration of the caves. I didn't go through a lot of the hardships and all the fun stories that come from these trips, but I did want to touch a bit about some of the science and the work that's been done. So we've actually had a number of publications now with the various members of our team, and literally have about 4 or 5 in review or sort of in the process, which are coming out. And our last trip, we had about 20 different ideas for other ones. So this is really, truly amazing time to be involved in these explorations. They're dependent on a huge team of people and researchers all collaborating together. And so certainly I help with leading the exploration and survey teams, but there's so many people that are part of those and the wider group that's part of this that makes it all happen. So many people, sort of too many to thank, but I just do want to mention that it certainly is a team effort. And, we owe these photos and the work to sort of a lot of different people who've been part of them over the last, 8 or so years. All right. Thank you very much.
Very good, Christian. It was very interesting. So are you signed up for Mars?
Yeah. No, the idea of a one-way ticket or whatever isn't.
Yeah.
Yeah.
Oh, well. There is a small fundraiser for Mars projects, and for $5 you could own an acre of land. So we own an acre of land on Mars, and it's been plotted on Google Earth, and it's in a crater 3,000 meters below the surface. So it's a very deep crater. So I don't imagine we'll have a lot of trespassers.
Nope.
No, very good presentation. Thank you.
Exciting. So,
yeah, Christian, thanks a lot. That was, first, it was incredibly interesting and very well delivered. So thank you very much.
Thanks.
Thanks, Christian. It's Peter here. That was great. Really enjoyed it. Learned a lot.
Thank you.
So,
any questions about any of the expeditions or about the topic itself?
So
I know there's a
Christian,
bit of a social caver gathering happening, and I don't want to keep people away from having a few drinks.
Christian, what kind of microbial life did you find?
So yeah, good question. I'm not the best to sort of describe all of them, but what I guess the main sort of thing that was found is a lot of different bacteria that are using alternative means of gaining energy. So they're using chemoautotrophy. So they're using the gas or metabolizing the rock itself to gain energy. So those are very, very interesting things to hear about. I didn't hear much more about the viruses. I think this is still work that's a little bit sort of in progress, but yeah, definitely there's a few different types of bacteria that are sort of metabolizing or using different pathways to gain energy.
Anybody else have any questions for Christian?
Oh,
Yeah, I had a question, Christian. You were talking about some of the flows that could come down from Mount Meager towards Pemberton, and you used a lot of terms that I didn't understand for the kinds of debris flows. Yeah, everything from the one you called for lava to debris or rock or ash. So those were like the layman's terms, but I'm wondering if you
Yeah.
could like describe those.
Sure. So there's a couple different types. There's I guess the pyroclastic flow, which is the lava flow that would come from that. And I guess that's going to be more localized to the area immediately around Mount Meager. The lahar is the volcanic mud flow. So we could see the volcanic debris and mud flows from the sudden melting of all the glacier ice there that would flow down the valley and potentially reach all the way to Pemberton. So there's those. And then the other one I showed, which was I said I might have used tephra or ash. So we're talking about the ash and debris that's carried from an explosion in the wind. So that was reaching all the way towards, into Alberta, going towards Vancouver. It was like quite a wide area that was. So those were, I think, the three different impacts that I talked about. Does that explain it?
Yeah, that's great. Excellent. Thank you so much for that. That was a great presentation and yeah, very well done. So thanks. Learned a lot.
Thank you.
Christian, did you come across any situations where you had like suddenly bad air, like while you were in there?
Yes. Yeah. So actually interesting thing was that helped guide a little bit of our risk management on future trips. In 2015, we had our most serious incident of bad air, and it was me. So just without getting too much into the details of it, that I sort of escaped by the skin of my teeth from a pocket of carbon dioxide within the East Crater Cave of Mount Rainier. So since then, we've adopted a number of different protocols and equipment to sort of emergency breathing devices and so forth. And then when we went back, we went with these SCBA units that we were able to further explore. So we have a few different strategies, but yeah, between that, one of our team that was just photographing. So me and Katie were in the West Crater Cave of Mount Rainier, working with the breathing apparatus to survey. And one of our team was trying to take a photo, and he just literally dipped his head like, half a meter below the threshold of carbon dioxide and literally fell backwards. It just passed out kind of almost instantaneously. So there's definitely been a few instances where it's been a challenge. And so actually, I was passionate enough about that and the data that we had collected that we wrote up a paper. So was accepted by Journal of Cave and Karst Studies just recently about the hazardous atmospheres in ambient air within a glaciovolcanic cave system. So we had a bit of discussion about the formation of those atmospheres and the persistence of them and sort of the life safety aspects of it too.
Very
Christian,
good.
back in the 1970s, there was a few people from Cascade Grotto who were exploring the ice caves of Mount St. Not like Mount St. Helens because it hadn't started yet, but the Mount Rainier.
Yeah, so the big study in Mount Rainier, Bill Loki, Bill Steele, there was a few others involved in a pretty big project, and that was the first major expedition to map the Mount Rainier system. They did quite a lot of work back then. Eugene Kiver was part of that work too. They did work on a little bit on Mount Baker as well. So they got pretty involved in doing that kind of work, and definitely laid the groundwork for some of the work that we are doing now. There was a fellow named Anderson who explored fern caves in the crater of Mount St. Helens before the 2004 to 2008 lava dome disrupted them all. So the system that we're talking about is new to those studies, which were in the late 90s. Yeah, you can actually find quite a bit from the Cascade Grotto and some of the stuff that was done back then. So yeah, good to mention that. Thank you.
Okay, wow, very good, Christian. Appreciate it, as I said, and I think maybe we'll end the official presentation and go to the caver chat if anybody's still around, so everybody can. I'm going to stop recording, and then we'll see what everybody has to say. Okay.
Yeah, turn all your videos back on, and we can say hi to each other.